Okay, this is it. This is another video on Fibonacci Fibonacci numbers, and so today we are going to talk about some special ratio known as metallic ratios. Metallic ratios. Okay, so in order to do so, let us consider a geometric interpretation. Consider a segment of line from A to some point B. So this this segment can be subdivided into two segments. The smaller AC and the larger one CB. So in addition, also or the bigger one can be subdivided into other segment from C to D, for example, and so on. Let us take equal segment, the congruent segment actually, like here can take D2 if this is D1 and this is suppose D0. So we can continue subdivision equally until dn minus 1, and this one is dn. Okay. So if we make equal subdivision, so we can end up with the CB, the size CB, length CB, equal to n times CD, length CD, with some indexing n greater than 1, and so on. So in this case, we need another condition. So if we suppose that the sequence, for example, let us take the sequence A, C, and CD, and AB. Suppose this sequence is geometric sequence. Geometric sequence. Let us suppose so. So in this case, we can get another condition. So ratio CD divided by AC, if this sequence is geometric, in case the middle term is the geometric mean of the extreme terms AC and AB. So in that case, we have CD over AC is going to be equal to AB over now CD. So now this makes another condition which is important because it will lead us to the expression of metallic ratio, which is actually CD over AC. So in that case, we can subdivide AB as into AC plus CB as we have indicated before, divided by the common denominator. So in this case, it's gonna be equal to sum of two terms. First ratio AC over CD, so plus CB over CD. So we can make a substitution here and then get so also this can be written as actually it is reciprocal of CD over IC, so that you can simplify or write CD over AC, metallic ratio actually. Now here we have CB, so I can use its equivalent expression here, n times CD divided by CD. So you can see that there is a way of simplifying and get the second term being exactly equal to n. So in this case, we have situation here. So we can simplify this ratio as it is a metallic ratio. You can call it mu n, and in this case mu n is going to be equal to 1 over mu n. So I add the n. So this is another interesting interesting equation, and we can solve in order to get what we have called the metallic ratio. Mu n is metallic ratio. Metallic ratio we are looking for. So we have denoted the mu n as indicating to indicate that it is a function of n actually if we solve for it. So now this we can solve it, and how can we do it? So you can multiply both sides of this equation by mu n on both sides. By doing so, let us see how it looks like. Both sides mu n. By doing so, we arrive at equation mu n over 2 equal to 1 plus multiplication here, then you have n times mu n. And what you have here is a quadratic equation, which is actually a characteristic function, as we are going to see later on. And you can solve it, and in general form, it can take the form mu n square minus n mu n minus 1 is going to be equal to 0. So now here we have two solutions for this equation, the sum of which is equal to n, and the product of which is equal to -1. And those two solutions are, so we have two possibilities. So one is a half, a solution for quadratic equation. So you have half of square root of sum square minus 4 times the product. So it means here you have sum square product here. So by substitution, so we get two values, half of sum n. So actually it is not n square but just n, and plus or negative half of square root. Now n becomes n square, so minus 1 minus 4 times minus 1 is going to be positive 4. So we have just two values. So one of them, it is half n, plus half of square root n square plus 4. So another one, another possibility, mu n is half of n minus half of square root of n square plus 4. So according to, to our problem, so the first solution, both are good solution of the quadratic equation, but for our problem, this one can be considered as not good solution. This one is a good solution, just because the ratio, this ratio, as it is a ratio of length, it must be positive. So as you can see, if we take difference here, so this number is less than this number, so that is less than 0 is because this number is less than 0, this one is less than 0, and it makes it good and it makes it bad for our equation. But for a quadratic equation we have here, both solutions are good solutions. So what we call metallic ratio is this one, which is good, and which is mu n is equal to half of n plus square root n square plus 4. Metallic ratio. Okay, so in relation with the Fibonacci numbers, so the relation can be found if we consider the properties of this metallic ratio. So reason why we're gonna move to the properties of these metallic ratios. Un, so let us write it over here. So properties of these metallic ratios. So one of the properties is common to all positive numbers. When you take a positive number like this ratio, this one, and you raise it to any power for k, starting from 0 and so on and so forth. In this case, it becomes a geometric sequence. Index is k. It becomes a geometric sequence, so that we have a state in which the numbers form a geometric sequence. Okay, so now one of the properties, let us call it P1, actually, P1. So it is this property, or this property with the black one, for k equal to 1, we have this metallic ratio. We're going to have Vk, V1, k with k equal to 1, so is equal to 1 over V1 plus n. Okay, so that is the property. So to prove, so this does not need the proof because it was given as the second condition as previously indicated. This is where it's coming from. So the second property, which is important for us, which needs more attention, is the fact that this sequence is such that uh, it is the sum of some kind of linear combination of the two previous terms. If we take vk plus the previous one times n, vk minus 1, so a multiple of the previous plus the most previous one, you're gonna get the general term of this geometric sequence. So there are many ways. So the first one, you can prove it just by setting k equal to 1. If we set k equal to 1 here, so you get this direction, the first one. Second one is the most important, so it needs more attention, is the fact that um, you can prove it in different ways, of course, but let me just prove it two ways to prove this. So I can take the first one and multiply both sides by the constant ratio, because here the constant ratio of this geometric sequence is just the metallic ratio. That one is the constant one, and the first term, which is you can call v0, is just 1. So now if we set, so the general term as vk is equal to, suppose, v naught times 2 power k. So in that case, when you set k equal to 1, so you get this relation, since it verifies it is equal, since q q is equal, the constant quotient is equal to the metallic ratio. Okay, so now, so the second proof, the first proof, of course, is I can take, let me prove proof of second property one way. So I can take multiply both sides of the first properties here by, can multiply by the power by k, k minus 1, both sides, q minus k minus power k minus 1. So q to k minus 1, q k minus 1, both sides. So what I get here is I have here mu n times mu n power k minus 1. So this is equal to 1 over mu n times mu n power k minus 1. So uh, oh, I forgot, of course, I forgot plus n. So I have to add n here, adding n. So it's gonna be now sum, it's gonna be equal to the sum here, n times 2 k minus 1. Okay, so now here, what I get here is mu n power k minus 1 plus 1 is gonna be equal to k. So here I have mu power n k minus 1. So as I have to divide by mu n, so it's gonna be minus 1 again plus n. So q is equal to mu actually. So mu n or k minus 1. Okay, so now here you can see that this one is mu n power k minus 1 minus 2 minus 1 minus 1 minus 2. So this is mu n power k. So equal to n times mu power k minus 1. Okay, so reason why in this case, as we know mu equal to q, and somehow q is v is v1, so we can write this one. This quantity is just vk. So reason why we have come to the end of the proof here, index n. We have come to the end of the proof of the second property, this identity. Because if I write this vk, so this one is going to be mu n power k minus 1 is going to be equal vk minus 2, and vk mu n power k minus 1 is going to be equal to k minus 1. Okay, so reason why we have come to the end of the proof. So another proof which is more interesting than this one looks like this. Like this. So I can take the second member and I show that is equal to the first member, first side. So A is equal to vk minus 2 plus n vk minus 1. So now this is equal to vk minus 2 is like mu n power k minus 2 plus n times mu n k minus 1. So this is, I can factor out mu n power k, because actually this is what I want, and I'm left with mu n power negative 2 plus n times mu n power negative 1. And then I can multiply here mu n k. I multiply by mu n and I divide by mu n again, and there is no change. Mu n minus 2 plus c n mu n minus 1. And if I do so, what will I get? If I do so, of course, this one and this one is gonna simplify each other, and I'm gonna get, let me use a different color here. So what I get here is mu n k over mu n times, now multiply inside, then mu n minus 1 plus multiplying this side becomes n. Okay, so now here we're gonna have in this case mu n power k over mu n, so times 1 over mu n plus n. Now what is this? This quantity is just this factor, the factor we have here. So this factor is equal to mu n according to the first property, or anyway, according to this equation is equivalent to this quantity being equal to mu n. Now I have to simplify this quantity and this one because it is mu n, and what I'm left with mu n power k. And what is mu n power k? So somewhere we have indicated mu n power k is vk, because v naught is equal to 1. So in that case, we have this is vk or q power k, or equivalent mu n power power k. And this is b, as you have started by a. A is equal to b. So which makes it the end of our proof. A is equal to b. Okay, now we have to end this metal equation here. So in the next video, we are going to show that, or to use this property number 2, as I have indicated, in order to find the general form of uh, Fibonacci sequence, the general term of Fibonacci sequence, how to solve such equation, because this identity leads to a difference equation we are going to solve by next time. So thank you very much for today.